So we are now going to discuss quadratic residues and introduce Legendre symbol and Jacobi symbol. Already we have introduced quadratic residues. Suppose AB an element of ZP star. P is some odd prime and A is not divisible by P. That means A is not congruent to 0 modulo P. So A is an element of ZP star means A is not congruent to 0 modulo P. Now A is said to be quadratic residue modulo P or a square modulo P if we can find an integer in ZP star, x belongs to ZP star, such that square of x is congruent to A modulo P. If no such x exists, then A is called quadratic non-residue modulo P. So this already we have introduced these things. Okay. Now set of all quadratic residues modulo P we denote it by QP, and the set of all quadratic non-residues are denoted by QP bar. Now, since ZP star does not contain 0, so 0 is neither a quadratic residue nor a quadratic non-residue. That means 0 doesn't belong to QP, and also 0 doesn't belong to QP bar. Now, in this regard, we mainly consider two problems in the theory of quadratic residues. So, given a prime, determine which A are quadratic residues modulo P. So identify the integers which are quadratic residues modulo P and which are not. And another problem is, given an integer A, determine those primes for which A is quadratic residues modulo P and those for which it is not a quadratic residue modulo P. Okay, so we will begin with some methods of solving the problem 1. Okay, first thing, suppose this example, suppose I have to find all the quadratic residues modulo A prime P. So P is given, P equal to 11, and we have to find all the quadratic residues modulo 11. Okay, so what we will do, so we will consider Z11 star. So what are the elements of Z11 star? The elements are 1, 2 up to 10. So all these elements in Z11 star, there are 10 elements, and we keep on squaring them. 1 square and reduce modulo 11. 1 square is 1 modulo 11, 2 square is 4 modulo 11, 3 square is 9 modulo 11, 4 square is 16. 16 means essentially 5 modulo 11. 5 square is 3 modulo 11, and then if you keep on squaring consecutive integers in ZP star, Z11 star, 6 square is essentially again 3, 7 square is 5, like that. Okay, so consequently quadratic residues modulo 11 are 1, 4, 9, 5 and 3, because they are essentially squares of some integer from ZP star. So 5 is square of 4, 3 is square of 5. So this 3, 5, 9, 4, 1, these are quadratic residues modulo P. Okay, and the remaining integers in this set in ZP star are quadratic non-residues. So these are quadratic residues modulo 11 and these are quadratic non-residues modulo 11. So this example illustrates the following theorem, that if P is any odd prime, then every residue system modulo P contains exactly P minus 1 by 2 quadratic residues and exactly P minus 1 by 2 quadratic non-residues modulo P. So P is an odd prime. If you consider ZP star, there are P minus 1 elements. P is odd prime means P minus 1 is even. Half of them are quadratic residues modulo P and half of them are quadratic non-residues modulo P. And the quadratic residues belong to the residue classes containing the numbers, these 1 square, 2 square, 3 square, P minus 1 by 2 whole square modulo P. So this is precisely these elements when reduced modulo P give the quadratic residues modulo P. So we are now going to give the proof. Already we know this fact. We have mentioned this fact earlier. Now we are going to prove this. So first note that if you consider any two elements, okay, from here, some x square and some y square. So they are distinct modulo p. Why? Because if x square is congruent to y square modulo p, then what we'll get? Then we get x square minus y square equal to 0 modulo p. That means x plus y into x minus 1, x minus y, x plus y into x minus y is 0 modulo p. Now mind that this x square y square are elements from here. So x and y, they lie within the range 1 to p minus 1 by 2, including 1 and p minus. X, y both arise in this range. Okay. Now this congruence, if this congruence holds, then we get this. This means what? P divides this. That means either P divides x minus y or P divides x plus y. Now if you consider x plus y, it lies within the range 1 to p. So this is an integer less than p, so p cannot divide x plus y. So this must be the case that p divides x minus y. Okay, so if we pick two elements from here, x square and y square, and if they are equal modulo p, then we are getting p divides x minus y. That means x is congruent to y modulo p, but x and y are both in this range, they are less than p, so it must be the case that x equal to y. So two different elements cannot be equal modulo p, congruent to modulo p. Okay, so if they are congruent, then we are getting a contradiction. Means essentially x and y themselves are equal. Okay, so first point we note all these elements are distinct. There are p minus 1 by 2 elements. These elements are distinct. No two of them are equal modulo p. So if you reduce modulo p, you get p minus 1 by 2 different elements of ZP star. Also p minus k whole square is k square modulo p. Square, if you take the square, it is k square modulo p. So if you take the next element, this is 1 square, 2 square, 3 square, p minus 1 by 2 square, then it will be p minus 1 by 2 plus 1 whole square. That means p plus 1 by 2 whole square. Like that, if you keep on doing that, means the next element is essentially same as this element. That means because this element is this element can be written in this way. Okay, the next element is p minus 1 by 2 plus 1 whole square. So p plus 1 by 2 whole square, and that can be written in this form. Okay, so every quadratic residue is congruent modulo p to exactly one of the elements in 1. So 1 square, 2 square, 3 square, p minus 1 by 2 whole square, they are when we reduce the modulo p, they are all distinct. And if you consider squaring other elements, means p minus 1 by 2 plus 1 whole square, p minus 1 by 2 plus 2 whole square, up to total p minus 1 elements, so p minus 1 whole square. So those remaining elements, those p minus 1 by 2 remaining elements can be written in this way, and essentially when reduce modulo p, the remaining elements, they will give you this one of these elements. Each of them will give one of these elements. Okay, so every quadratic residue is congruent modulo p to exactly one of the members in this. Okay, so from this you can argue that in ZP star we have p minus 1 elements, and out of them p minus 1 by 2 elements quadratic residues, and those are given by this, and remaining p minus 1 by 2 elements are quadratic non-residues modulo p. Okay. So that is, so if p equal to 3, then the quadratic residues modulo p is only 1. P equal to 5, then 1 and 4. P equal to 7, 1, 2, 4. So this you can verify. This already we have considered in that example. You can find this. Now we are going to discuss the introduce the Legendre symbol and Jacobi symbol. So what is Legendre symbol? Legendre symbol, suppose AP be any odd prime and A be any integer. Now Legendre symbol we denote it by A over P within first bracket. This notation A over P, this is Legendre symbol of A modulo P. How we define this is essentially either this is either 0 or 1 or minus 1. Okay, so this Legendre symbol A modulo P is 0 if P divides A. If P is a factor of A. It is 1 if it is square modulo P, that means quadratic residue modulo P, means A belongs to QP. And if it is minus 1, then if A is quadratic non-residue modulo P, then it is minus 1. So Legendre symbol is 0 if P divides A, 1 if A is quadratic residue modulo P, and minus 1 if A is quadratic non-residue modulo P. So you can see that 1 is always quadratic residue modulo P for any prime. So this 1 over P, this symbol is always 1. If you take square, some square over P, that is also always 1. 7 over 11, this 7 over 11. So modulo 11. Modulo 11, if you consider modulo 11, 7 is quadratic non-residue. So 7 over 11, this Legendre symbol is minus 1, like that. So 22 over 11, so 22 is divisible by 11, so this is 0, like that. Now properties of Legendre symbol, this actually we need these properties, okay. We need these properties while we discuss Revi's crypto system and also Goldwash and Michaelis crypto system, this we are going to use this fact. So what this states, suppose P be any odd prime and A be two integers. So then the Legendre symbol has the following properties. Legendre symbol has the following properties. A over P is congruent to A to the power P minus 1 by 2 modulo P. A over P is congruent to A to the power P minus 1 by 2 modulo P. In particular, if you take 1 modulo P, 1 modulo P is always 1. Minus 1 modulo P is minus 1 to the power P minus 1 by 2. So you can show this equality. So we are going to show this equality holds. So generally A over P, this Legendre symbol is congruent to A to the power P minus 1 by 2 modulo P. Okay, now 1 is always quadratic residue modulo P. So Legendre symbol of 1 is always 1 for any prime. And for minus 1 is quadratic residue modulo P, provided P is congruent to 1 modulo P. That means this prime is 4k plus 1 type. And minus 1 is quadratic non-residue modulo P, means P is congruent to 3 modulo 4, which is 4k plus 3 type. See, if P is 4k plus 1 type, what we get? P is 4k plus 1 type means this is 4k plus 1 minus 1. So this is even power. So it is 1. Legendre symbol is 1. So in that case, this is minus 1 is quadratic residue modulo P. If P is congruent to 3 modulo P, that means 4k plus 3 type. P is 4k plus 3 type. If you put 4k plus 3 here, 4k plus 3 minus 2 divided by 2. That means odd power. 4k plus 3 minus 2 means 4k plus 2 divided by 2. That means twice k plus 1. Okay, so odd power. So you are getting this value minus 1. So minus 1, Legendre symbol of minus 1 is minus 1. Minus 1 in that case, in this case, minus 1 is quadratic non-residue modulo P. Also, we have this property that Legendre symbol is completely multiplicative. Multiplicative, what does this mean? Means AB, Legendre symbol of AB modulo P is Legendre symbol of A modulo P into Legendre symbol of B modulo P. Hence, if A is element of ZP star, A square modulo P is always 1. Okay. And if A and B are congruent modulo P, then they will have the same Legendre symbol. A over B, P and B over P also equal. Okay, let us, we have some more properties also. Okay, let me complete the properties first. Okay, so far what we have stated, this property, this is a very crucial property. It is called actually Euler's criteria. We are going to give a proof of that. Okay, now this is completely multiplicative. We are going to show this also. This property, this is essentially states when 2 is going to be under which condition, under what type of prime 2 is quadratic residue modulo P, and under what conditions on P 2 is quadratic non-residue modulo P. We are going to show that 2 over P is minus 1 whole to the power P square minus 1 by 8. So if means 2 over P, this Legendre symbol is 1 if this is even power, right? And the condition for this to be even number is P is congruent to 1 modulo 8 or 7 modulo 8. That means P is of the form 8k plus 1 type. If you put 8k plus 1 type, this will be even power, 8k plus 1 type or 7k plus 1 type. And 2 over P is quadratic non-residue modulo P, means T over P is minus 1. That in that case, 2 will be quadratic non-residue modulo P if P is of the form 5k plus 8 or 3k plus 8. This we are going to show. Okay, so this does not automatically follow from Euler's criteria. It does not automatically follow from Euler. This is P minus 1 by 2 and this is congruent relation. Okay, this is P square minus 1 by 8. We are going to show this. And the law of reciprocity, quadratic reciprocity, it says that if you have two distinct odd primes, Q is odd prime distinct from the prime P, then P over Q, this Legendre symbol, equal to Q over P times minus 1 to the power P minus 1 Q minus 1 divided by 4. Okay, so you can rewrite in this way also. P by Q, this Legendre symbol multiplied by Q by P equal to minus 1 whole to the power P minus 1 into Q minus 1 by 4. Because essentially this value are either plus 1 or minus 1. Okay, and it is not 0 because Q and P are distinct primes. So these values are plus 1 or minus 1. So this I can put in on the left hand side also. So P by Q, Legendre symbol P by Q, product Q by P equal to minus 1 whole to the power P minus 1 by 2 into Q minus 1 by 2 divided by 4. So we have this result, simplified result, P over Q equal to Q over P unless both P and Q are congruent to 3 modulo 4. In which case P over Q equal to minus Q over P. Okay, so if both P and Q are of the form 4k plus 3 type, then P over Q equal to minus Q over P. Okay, and Jacobi symbol, I will discuss this later. Okay, first let us give the proof of those results. Okay. So I can prove Euler's criteria. This is my Euler's criteria. I'm going to prove this thing. Okay. So P be an odd prime. Then we are going to show for all A over P is congruent to A to the power P minus 1 by 2 modulo P. It actually, to prove this, we are going to use Fermat's little theorem. Fermat's little theorem states that if P does not divide A, that means P and A are co-prime, then A to the power P minus 1 is congruent to 1 modulo P. From here, I can get A to the power P minus 1 minus 1. It can be written as A to the power P minus 1 by 2 plus 1 into A to the power P minus 1 by 2 minus 1. So this is congruent to 0 modulo P. That means A to the power P minus 1 by 2, this value is either plus 1 or minus 1 modulo P. Okay, so this Euler's criteria, we are going to show that this Euler's criteria now using this fact. Okay, so first case, suppose A is 0 modulo P, that means P divides A. Then left hand side it is 0, Legendre symbol by definition. When P divides A it is 0. Right hand side, if A is 0 modulo P, that means A is divisible by P, this side is also 0. So this case A equal to 0 modulo P, this case follows trivially. Now case 2, suppose A over P is 1. This value, this Legendre symbol is either 0 or 1 or minus 1. So accordingly I discuss 3 cases. Case 1 is trivially follows. Case 1 trivially follows the result. Case 2, suppose A over P, this Legendre symbol is 1. We have to show right hand side is also 1. Now we have seen that right hand side A to the power P minus 1 by 2, this is the value is either plus 1 or minus 1. Okay, by using Fermat's little theorem, we have already seen that right hand side value is plus 1 or minus 1. We have to argue that if A over P Legendre symbol is plus 1, then in this case right hand side also is plus 1. How we are going to show that? Okay, so if it is plus 1, that means this is quadratic residue. A means A is quadratic residue modulo P. That means there exists some integer x in ZP star such that square of x is A modulo P. A is square modulo P. That means some x exists in ZP star such that x square is congruent to A modulo P. Therefore, A to the power P, right hand side A to the power P minus 1 by 2, put the value x square to the power P minus 1 by 2. This value is x to the power P minus 1. Now by Fermat's little theorem, we know that if x is an element of ZP star, then x to the power P minus 1 is congruent to 1 modulo P. By Fermat's little theorem. Okay, so by Fermat's little theorem, we get this value is 1 modulo P. This value is 1 modulo P. This value is 1 modulo P. So when A over P is 1, then A to the power P minus 1 by 2 is also congruent to 1 modulo P. Therefore, in this case, this result follows. Now the last case, A over P is minus 1. A is quadratic non-residue modulo P. Okay, so we have to show in this case also right hand side will be minus 1. How to prove that? Now consider this equation, this congruence, this equation, this polynomial x to the power P minus 1 by 2 minus 1. So what is the degree of this polynomial? Degree of this polynomial is P minus 1 by 2. Now, if you consider this congruence equation, polynomial equation, this equal to 0 modulo, congruent to 0 modulo P, then by Lagrange's theorem, this equation, this x to the power P minus 1 by 2 minus 1 equal congruent to 0 modulo P, this has at most P minus 1 by 2 solutions. Okay, when P is prime and you have a polynomial equation with coefficients, integer coefficients. If you have polynomial equation with integer coefficients and your congruence equation is modulo some prime or prime, then this has at most n many solutions where n is the degree of the polynomial fx. So in this case, this is also this equal to 0 modulo P. This is polynomial equation, degree P minus 1 by 2 and with integer coefficients. So this equation has at most P minus 1 by 2 solutions. At most P minus 1 by 2 solutions. Now we know that the P minus 1 by 2 quadratic residues, P minus 1 by 2 quadratic residues are solutions of this equation. So it has p minus 1 by 2 many solutions at most. And we have p minus 1 by 2 many quadratic residues, and all of them are actually solutions of this equation. Already we have seen here. If it is quadratic residue modulo p, if it is quadratic residue, that means square. So this if A is quadratic residue modulo p, then this equation holds. A to the power A is a solution of this equation. Okay, so there are p minus 1 by 2 quadratic residues modulo p. All of them are essentially solution of this congruence equation, and it has at most p minus 1 by 2 many solutions. So if we have any solution, that solution, any solution of this that is essentially a quadratic residue modulo. All the solutions of these are quadratic residues. It has at most p minus 1 by 2 many solutions, and all the p minus 1 by 2 quadratic residues are solutions of these. So any solution of this is essentially quadratic residue modulo. So if you take this A over P to be minus 1, that means A is non-quadratic residue modulo P. So it cannot be a solution of this. That means this A does not satisfy this equal to 0 modulo P. So A to the power P minus 1 by 2 is not congruent to 1 modulo P. Okay, but by Fermat's little theorem, we have observed A to the power P minus 1 by 2, this value is either plus 1 or minus 1. Already we have seen here argument from Fermat's little theorem. This A to the power P minus 1 by 2 modulo P's value is either plus 1 or minus 1. Okay, so here we have argued that A to the power P minus 1 by 2 cannot be 1 modulo P in case A over P is minus 1. That means A is quadratic non-residue modulo P. Okay, so it attains the other value, minus 1. So A to the power P minus 1 by 2 is congruent to minus 1 modulo P. That means it agrees with this value, A over P. So in this case also, Legendre symbol A over P equal to A to the power, congruent to A to the power P minus 1 by 2 modulo P. Okay. Okay, I think argument is clear. In this case, argument is clear. When it is Legendre symbol is minus 1, A is not quadratic non-residue. A is not a quadratic residue modulo P. Minus 1 means A is quadratic non-residue modulo P. A is quadratic non-residue modulo P means this equation, A cannot be a solution of this equation. Why? Because it has at most P minus 1 by 2 solutions, and all the P minus 1 by 2 quadratic residues modulo P are solutions of these. Okay, so if A is non-quadratic residue modulo P, then it cannot be a solution of this. So we have P minus 1 by 2 many quadratic residues modulo P. Each of them is a solution of this. And it has at most P minus 1 by 2 many solutions. So all the quadratic residues modulo P are the solutions of these. All these P minus 1 by 2 many. So if A is non-residue modulo P, quadratic non-residue modulo P, it cannot be a solution of these. Otherwise, it will contradict this fact that it has at most P minus 1 by 2 solutions. Okay. So in this case, it is not congruent to 1 modulo P, but its value is either plus 1 or minus 1. So it should be minus 1 modulo P. This completes the proof. Now, next problem is, it is completely multiplicative. Completely multiplicative in the sense that AB modulo P is, its Legendre symbol is A modulo P into B modulo P. Why we say completely multiplicative? Completely multiplicative means there is no restriction on AB. Say for example, when we have proved that Euler's phi function is multiplicative function, we didn't use this word completely multiplicative. We just said it is a multiplicative function. Multiplicative function means GCD of AB should be 1. So there is no restriction here. When you say AB modulo P equal to A modulo P into B modulo P, it is completely multiplicative means there is no restriction. We don't need the condition that GCD of AB equal to 1. For Euler's phi function, to prove Euler's phi function completely multiplicative, we have a restriction that AB, this GCD is 1. Okay. So Legendre symbol completely multiplicative. You have to prove that. Case 1, suppose P divides A or P divides B. So in that case, P divides AB. So in the left hand side, this is 0. And right hand side also 0, because if P divides A, this part is 0. So essentially the whole part is. So in this case, it actually follows trivially. Okay. So if this is the case, P divides A or P divides B, then P divides AB. From P divides AB, you get this part is 0. From this P divides A, you get this 0, or for P divides B, you get this 0. So both sides 0. So we get this. We get this. When P divides A or P divides B, we get this relation holds. Now suppose P does not divide A, P does not divide B. So in that case, P does not divide AB. Now by Euler's criteria, we can say AB modulo P, this Legendre symbol is congruent to AB to the power P minus 1 by 2. Okay, so I am applying Euler's criteria. This is my Euler's criteria. A over P Legendre symbol, A over P is congruent to A to the power P minus 1 by 2 modulo P. So on AB I am applying. So AB modulo P, and this Legendre symbol is AB to the power P minus 1 by 2 modulo P. So that I am using. Okay, so AB modulo P, this Legendre symbol equal to AB to the power P minus 1 by 2, congruent. So this is multiplicative functions, A to the power P minus 1 by 2, B to the power P minus 1 by 2. Now again apply Euler's criteria. So this is congruent to A over P, this is congruent to B over P modulo P. Now in this case, we have to show exact equality holds, not congruence. We have so far we have obtained this AB modulo P, this Legendre symbol is congruent to A over P into B over P, this Legendre symbol multiplication modulo P. Why equality holds? Because if you see that each of these Legendre symbols, AB modulo P, A modulo P, B modulo P, these are Legendre symbols. Okay, and each of them are either plus 1 or minus 1. They cannot be 0 because I have put the restriction. P does not divide A, P does not divide B. So P does not divide AB. So none of them is 0. So their values are either, they attain the values either plus 1 or minus 1. So if you take the difference AB over P minus A over P, B over P, so their difference is either 0, 2 or minus 2. If they take the values 1 or minus 1, then their difference is either 0, 2 or minus 2. Now their difference from this relation, their difference is 0 modulo P. Their difference is divisible by P. So their difference cannot be 2 or cannot be minus 2 because P is an odd prime. Okay, so the difference must be 0. And that implies that exact equality holds. A over P, AB over P equal to A over P, B over P. So it actually, this equality actually follows from this fact that their difference, if you take the difference is either 0, 2 or minus 2 because each of them takes the values 1 or minus 1 only. Okay, under this restriction. So this value is either 0, 2 or minus 2. But the difference, this difference is essentially 0 modulo P. P cannot divide 2 or minus 2, so P must divide. Means it should be 0 modulo P. P must divide this. Okay, the value should be 0. Now, so we have mentioned that 1 modulo P is always 1. 1 modulo p, this Legendre symbol is always 1, but minus 1 modulo p, this value, and 2 modulo p, this value, when this Legendre symbol is 1, when this Legendre symbol is minus 1, under what condition on p. And this is also what are the conditions on the prime p for which 2 is quadratic residue modulo p, that means this is 1, and 2 is quadratic non-residue modulo p. So those conditions are given by this. So this one is easy. Minus 1 modulo p, this Legendre symbol by Euler's criteria, we get this is congruent to this is congruent to minus 1 to the power p minus 1 by 2 modulo p. Okay, so this side is the value, this is Legendre symbol, value is either 1 or minus 1. This side also minus 1 or plus 1. Okay, so you take the difference is 0 modulo p, and by the same reasoning as the earlier proof, their difference either takes the value 0, 2 or minus 2. But p cannot divide, p actually divides their difference. So p cannot divide 2 or minus 2, p divides, so their difference must be 0. Okay, using the same reasoning here, we can it follows that exact equality holds. By Euler's criteria, if you apply Euler's criteria, we get this congruence relation modulo p. But by that reasoning, you get equality. Now, if this equality holds means what? So this is 1 if p is 4k plus 1 type. 4k plus 1 type. The p is congruent to 1 modulo 4. That means multiple of 4 plus 1 type p. P is a prime, primes, odd primes. Odd primes means all the integers, you can generate all the integers with the recurrence 4k, 4k plus 1, 4k plus 2, 4k plus 3. Now 4k and 4k plus 2, they are even numbers, 4k plus 1 and 4k plus 3. So all the primes are either 4k plus 1 type or 4k plus 3 type. If your prime, this prime is 4k plus 1 type, then minus 1 is quadratic residue modulo p. And if the prime is 4k plus 3 type, then it is quadratic non-residue modulo p. So Legendre symbol is minus 1. Okay, so next is condition, means when 2 is quadratic residue modulo p and when it is quadratic non-residue modulo p. Okay, so the condition is 2 over p is equal to minus 1 whole to the power p square minus 1 by 8. How can I prove this? We consider the following p minus 1 by 2 congruences. Okay, so p minus 1, if you take modulo p, that is p minus 1 is actually minus 1 modulo p. So minus 1 I can write in this way, 1 into minus 1 to the power 1. Then 2 is 2 modulo p. So 2 is into minus 1 whole square. Then p minus 3 I write in this way, 3 into 1 minus 1 to the power 3. 4 into 4 is congruent to 4 times minus 1 whole to the power 4. R is congruent to p minus 1 by 2 minus 1 whole to the power p minus 1 by 2. Okay, so 1, 2, 3, 4 up to p minus 1 by 2 I am writing this. Okay, so 1, 2, 3, 4 p minus 1 by 2, and this R is either p minus 1 by 2 or p minus 1. So all these elements are, the first one is, this is p minus 1, 2, 3, 4 like that, but if it is odd, it is p minus 1 I am writing, p minus 3 I am writing. So if it is even, then it is p minus 1 by 2, p minus 1 by 2, 2 here 2, 4 here 4. So if it is even, then p minus 1 by 2, R is p minus 1 by 2, otherwise it is p minus 1 by 2. Okay, so we consider this p minus 1 by 2 congruences. Now if you multiply all of them, right hand side all multiply, then you get 2, 4 like that, 2, 4, 6 up to p minus 1. If you multiply all of them, rearrange 2, 4, 6 up to p minus 1. All the elements are here. 2, 4, 6 up to p minus 1. And on the right hand side, you get this is congruent to 1, 2, 3, 4 up to p minus 1 by 2. That means factorial p minus 1 by 2 into minus 1 whole to the power 1 plus 2 plus 3 plus 4 plus up to p minus 1 by 2. This value you get. So this are many this p minus 1 by 2 many congruences. When you multiply, you get 2, 4, 6 p minus 1 congruent to factorial p minus 1 by 2 minus 1 whole to the power this APC, this 1 plus 2 plus p minus 1 by 2. So this is essentially equal to p square minus 1 by 8. And this is factorial p minus 1 by 2. If you take 2 common from each of this p, there are p minus 1 by 2 elements. So 2 to the power p minus 1 by 2 and factorial p minus 1 by 2 this side. Now this factorial p minus 1 by 2 I can cancel out from both sides because p and this factorial p minus 1 by 2 they are co-prime. This factorial does not contain p as a factor. So p and factorial p minus 1 by 2 are co-prime. That is, it is not congruent to 0 modulo p. So both sides I can cancel out and we get 2 to the power p minus 1 by 2 is congruent to minus 1 to the power p square minus 1 by 8 modulo. This should be congruence relation. Okay, the congruence, this is also congruence. So we get this. Okay, now we are left with the proof. Just we have to show that equality holds. By the same reason, you can argue equality holds. If you take take the difference of this and this side value, this side value is essentially by Euler's criteria. If you use the Euler's criteria, this equal to 2 over p modulo p. So essentially, we are getting 2 over p. This Legendre symbol 2 over p is congruent to minus 1 whole to the power p square minus 1 by 8 modulo p. Now this value is plus 1 or minus 1. This value is also plus 1 and minus 1. So you can argue that the equality holds. Okay? This equality holds. And from here you can say that when 2 is quadratic residue modulo p, when it is quadratic non-residue modulo p. So the condition on this p is when it is even. When it is even, when p is 8k plus minus 1 type, and when it is 8k plus minus 3 type, it is odd. So this Legendre symbol is 1 when p is 8k plus minus 1 type. It's 8k plus 1 type or 8k plus 7 type. Minus 1 modulo 8 means 7 modulo 8. Okay. So p is 8k plus 1 type or 8k plus 7 type. Then it is 2 is quadratic residue modulo p. And if it is the prime is 8k plus 3 type or 8k plus 5 type, when minus 3, p is congruent to minus 3 modulo 8 means p is congruent to 5 modulo 8. Okay, so if p is for 8k plus 3 type or 8k plus 5 type, then this is odd and this value is minus 1. So 2 is quadratic non-residue modulo. Okay. So Jacobi symbol. Let us now introduce Jacobi symbol. Jacobi symbol is essentially the generalization of Legendre symbol. Generalization of Legendre symbol. So if you know the prime factorization, n suppose n greater or equal to 3 be an odd integer with prime factorization this. So Legendre symbol we have seen it is a over p. P is some odd prime. Jacobi symbol is a over n. N is any odd integer. Any odd integer means it need not be a prime. If it is prime, then Jacobi it is Legendre symbol. A over n when n is any integer not a prime. Okay, n is not a prime. Then this symbol, same symbol, but this symbol is called Jacobi symbol. Name is different when it is a composite number. N is composite number. When it is prime, it is Legendre symbol. So this is, so if you know the prime factorization of n to be this p1 to the power e1, p2 to the power e2, pk to the power ek, then Jacobi symbol a over n is defined in this way. A over n is means each Legendre symbol you calculate. A over p1 when it is prime it is Legendre symbol. A over prime to the power e1, a over prime p2 to the power e2, a over prime pk to the power ek. So this is how Jacobi symbol is calculated using the Legendre symbols. If n is prime, then Jacobi symbol is just the Legendre symbol. properties of Jacobi symbol also we have several properties of Legendre symbol, Jacobi symbol. A over n is 0, 1 or minus 1. The Jacobi symbol is also 0 or 1 or minus 1 because essentially it is product of some Legendre symbols. So Legendre symbols, since Legendre symbols are 0, 1 or minus 1, Jacobi symbol is also attain these values only. And if A means A over n is 0, this Legendre symbol is 0 if GCD of n is not 1, means A and n are not co-primes. When A and n are not co-prime, A contains n as a factor or n contains A as a factor, in that case it is 0. Okay. And AB over it is also multiplicative, completely multiplicative. AB over n is A over n, B over n. Not only that, we can show A over mn equal to A over m, A and B, A over n. This. Also, if A and B are congruent modulo n, then their Jacobi symbol are also same. 1 is always, Jacobi symbol of 1 is always 1. And minus 1, Jacobi symbol of minus 1 is equal to, means like Legendre symbol, whatever results we have for minus 1 and 2, here also we have the same result. Minus 1 modulo n, this Legendre symbol is minus 1 to the power n minus 1 by 2, equality rules. And 2 over n, 2 is, this also same result as Legendre symbol. Minus 1 to the power n square, 2 over n is equal to minus 1 to the power n square minus 1 by 8. Okay, and quadratic reciprocity law, means for Legendre symbol we haven't proved the quadratic reciprocity law. Okay, for Jacobi symbol also we have this relation, m over n over n equal to minus 1 whole to the power m minus 1, n minus 1 by 2. Means these three conditions, these three, the last three, this one, and this one, all these three we have proved for Legendre symbol. For Jacobi symbol also same result holds. We are going to give the proof of those also. Okay. However, Euler's criteria, like for Legendre symbol we have Euler's criteria. For Jacobi symbol we don't have this type of Euler's criteria. So using Euler's criteria, we have proved this relation, these three, these two equations, these two relations using Legendre symbol. For Legendre symbol, we have proved this using Euler's criteria. But for Jacobi symbol, you cannot do that. Means that approach will not be useful in proving this for Jacobi symbol. Okay, we will discuss the proof. We will discuss the proof. Next is okay. Here we have mentioned, we have actually illustrated here how to evaluate Jacobi symbol. How to evaluate Jacobi symbol? Let me check once. Jacobi symbol computation. Jacobi symbol computation. Okay. So to compute the Jacobi symbol, we utilize this result, and also this quadratic reciprocity law. Means here the condition of mn for Jacobi symbol is m and n are two distinct odd integers. Their GCD should be 1, otherwise it will not hold. Means m and n are odd integers and their GCD must be 1. Okay, so we keep on using this result and this result while computing the Jacobi symbol of an integer. How to do that? Suppose n be any odd integer and a we have to find the Jacobi symbol of a over n, and a we write in this way, 2 to the power some e times a1. So all the powers of 2 we separate. Okay, so 2 to the power e and a1 is some odd integer. So applying properties of Jacobi symbol, what we can write, a over n is 2 to the power e into a1 over a. By multiplicative property, I can write in this way, 2 to the power e modulo n and a1 by n. These two Legendre symbol, Jacobi symbol. Now this one is essentially same as 2 over n raised to the power e, and this one I can use the quadratic reciprocity law. Quadratic reciprocity law. So this one will be equal to a1 over n will be equal to n1 over a. A1 over n equal to n over a1 into minus 1 whole to the power a1 minus 1 into n minus 1 divided by 4. This is n. This should be n. A1 minus 1 into n minus 1 divided by 4. And n I can just we take the reciprocal of this and multiply with this factor. And every time we can reduce. If n is larger than a1, we can reduce so that this Jacobi symbol keep on reducing in size. And this one I can calculate, just check whether what is the form of n, and directly you can utilize this result. If n is 8k plus 3 type or 8k plus 5 type, means you just divide this n by 8 and check what is the remainder. Okay, if it is 8k plus 3 type or 8k plus 5 type, then you can simply write replace 2 by your n by minus 1. And if it is plus minus is 8k plus minus 1 type, then you can replace it by 1. Okay, so that is the strategy to compute the Jacobi symbol. Okay. So this observation yields the following recursive algorithm. Recursive algorithm, I have the algorithm written here. You can just go through it. Okay. So the execution is something like that. Suppose I want to calculate 158, Jacobi symbol of 158 modulo 235. So 158 modulo 235. So I extract the powers of 2 from here, means so it is 2 times 79. So 2 modulo 235 and 79 modulo 235. Now 235 it is 8k. If you divide 235 by 8, this is remainder is 3. So this value is minus 1. Using that property of 2, I can directly calculate this minus 1. Okay, so it is 8k plus 3 type. 8 into 29 plus 3 type. So it is minus 1. And here I will take the reciprocal and multiply with this. So it is 235 divided by 79 minus 1 whole to the power 79 minus 1, 235 minus 1 divided by 4. Now you simplify. What is the sign of this? This is actually calculate. This give me a minus 1. Okay, so this is odd, minus 1. And this one I can further reduce. So 79, you divide 235 by 79, take the remainder. So this is 77. 77. So this is reduced this way. Now, so what I get ultimately by calculating, simplifying this one simplifies to 77 by 79. Now again I use the quadratic reciprocity law. That means 79 divided by 77 into minus 1 to the power 79 minus 1, 77 minus 1 divided by 4. Okay, and this value essentially gives me 1, and 77 and 79 is larger than 77. You reduce it and you get 2. 2 divided by 77. Now 77, I divide 77 by 8 and I check it is 8k plus 3 type or 8k plus 5 type, so it is minus 1. Okay. So this is the algorithm, and this algorithm Jacobi symbol computation or Legendre symbol also, that is same algorithm. When you take the prime, take the modulus to be prime, it is Legendre symbol, otherwise it is Jacobi symbol. You utilize this fact. Essentially those properties, those properties gives you the simplification. Those properties means n is 8k plus 1 type or 8k plus 3 type, essentially gives you. Then this is a polynomial time algorithm. Okay. Okay, so here let us stop here. Okay, let us stop here.